Okay. The next speaker is Giovanni Naldi from University of Milan. He will talk about measurement and processing of mental workload from EEG sensors. One example.
Thank you, and we can start. Okay. So I think also is a break. So first, thank you for this opportunity, and I think it's a break among very complex diseases, very interesting talk, and it's a break. Why? Because now the problem is very different. Okay, is not invasive mathematics, but the goal is different. I apologize, but it's not a complex diseases, but is a particular problem. But is also a non-invasive mathematics and use, sorry, the EEG data. What is the problem? So it's a work in progress with Alessandro Benfenati and at University of Milano and Wongo, so from a company, a little company, a startup called Mensior. And the reason is the following. So the problem is the following. Suppose you have the possibility to have a recent device in order to have a single channel. So it's a nightmare for clinical people because you have a single channel, but we have a wearable device. So it's possible, for example, as you show you in the next slide, to embed in some helmet, for example, this very simple single electrode device, and it's possible to record something. It's possible to record something, but you are not in a lab, you are not in an hospital, you are not in some office, but you are essentially in a very complex environment. So we have a lot of noise, and you have a lot of things to consider if you want to extract something. And what we want to extract? We want to extract very basic brain waves. So the gamma, beta, alpha, theta, and so on. As in the talk of yesterday of Professor Daniela Calvetti, very interesting because more or less we have the same problem. We want to extract something, but now the device is very simple. We have no more electrodes, or a single electrode, no more wires. So it's possible to use effectively in every day, if you want. For electrocardiogram, you know, exists Holter, and it's possible to record for many hours something about your heart, okay? But now you want to record something about your brain waves. And so during the behavior, your activity, and so on. And this is a problem, the first step. And the company proposed me how to possible to extract by a very simple device, single electrode or something. Okay. And the second thing is focus on a particular problem. The particular problem regards the workers. So suppose there is a lot of problem for attention, for example, in order to hold the health and the safety of the workers. For example, if you consider something regarding the stress, the attentions, the fall asleep during your work. So how is possible to do that? So here the project is to embed this kind of single electrode things in a helmet, for example, try to understand if there is something which is not good for the worker. So there is a lot of fail during the work, so there is a lot of problem, and this is the project, okay? So the device is very simple. We need to have a wearable device, and we need to have also a chip device, and we want to perform some statistic analysis of brain waves in order to understand if possible to develop some index such that it's possible to say, okay, there is some problem now for the workers, so it's possible to have to do some action. So our framework, real-time processing, because the data go from the device to the mobile, and the possibility to have data for a long time. So we need a wearable and economical device. Okay, we are not in the case of a clinical study where you possible to use very simple, very complex device, or you have some other data. So you have many channel. It's possible to use, for example, something like principal component analysis, independent component analysis, so on and so forth. And now you have very simple data because it's from one electrode. But you have high noise, and you want to have some automatic artifact management. Because it's not possible to do something like, okay, I call my favorite neurologist and say, okay, from the visual aspect, please try to avoid some artifacts. I try to select some artifacts and so on. So it's not possible to do it. So this is our framework, okay? And in order to have a real-time processing, you need effective analysis tool and a low computational cost. And for data compression, because you have data for a long time, you need something for data compression. So as in the talk about yesterday, the Prela tool is exactly the same things. You want to represent in a sparse way our data, okay? So first, effective analysis tool, computational cost has to be low. So real-time processing, data compression, so sparse representations. And the case of economical device is bad from one point of view, because you have only few data if you want, but it's possible to do some statistical study. Okay, for example, for some workers during some days, it's possible to follow many workers and understand what is the bad situations. So with quality of the data, because because if you have a garbage in, it's possible to have a garbage out. So the quality of data is important. Now, the quality of the data means how many information is possible to extract by our poor single electrode. Okay, this is a problem. We start with the problem. Will not end the story, but I want to show our way. Okay. And so, first step, you consider the signal as a sun. So the signal, for the signal, I mean the raw data from the single device here. This is an example of this kind of device. So it's possible to have an electrode here, and it's possible to have a record, and by Bluetooth, it's possible to transmit to a mobile. Okay, and also exist this helmet. Because we have embedded this kind of a device inside the helmet. Okay, so we have a raw data, and composed by real signal. So the real signal means the real EEG. Underline, if you want, our biological signal. So the real signal, okay? But we have a biological artifact. And also you have some noise due to the electrode. So for the noise to the electrode, you base on some software from producers of the electrode, of this kind of device, and more or less we have a Gaussian noise, something like that. But there is something at the beginning when you record the data from the single electrode. There is something also from the device. So it's not so effective electrode noise, but biological artifact, yes. And there is a huge amount of reference if you consider the EEG literature about the noise artifact classification and so on. So is a huge amount of references. Okay, but the classical, if you want, the classical workflow is something like that. We have some EEG data, consider a single channel. We have some processing, so means that you consider artifacts, okay? And I asked to my colleague, and more or less the answers is, okay, the best up to now is the visual, the visual artifact removal. Okay, so exist a lot of possibilities, but seems I asked my colleague explain some kind of things, and more or less the answer is the best for us is some visual artifact removal. Okay, it's not so good for me, but okay, I try to continue. So and I identify in the wavelet-based approach something which is useful both from the spiral representations, as mentioned yesterday in a talk, because it's possible to have a time frequency compression of a signal, and it's possible also to use some autoencoder idea, because it's possible to have a compression of a signal, and we have a fast algorithms with a lot of algorithms. Also, there is something also for the mobile, if you want. And the second thing is how to understand the artifactual patterns in the time frequencies domain. So the question is, for the compression, this is no problem, because since that's also for each channel, if you clean from artifacts, it's very easy to have we have a lot of family of wavelets or wavelet packets in order to have some beautiful compressions, okay? But you need a pre-processing step. And then usually, if you look to the literature, there is a lot of training data, and there is some machine learning device at some point, okay? So support virtual machines or extreme learning machine or deep learning, something like that. So we have a feature, and then you develop something, okay? This is the new fashion, okay? But I want to also as a first attempt, to avoid also the classifier at the moment, and I try to understand if all information is just coded in our wavelet expansions. So my question is now, it's possible to consider as a first step, as a first attempt, only the information coded in the wavelet expansions, okay? And then it's possible also to focus on which is the best wavelet. You have to use wavelet or wavelet packs and so on, okay? But the first thing is to consider how to consider algorithms for denoising artifacts and other, okay? And also how to perform some nonlinear selection, because the transform is linear, but the selection is nonlinear. It's a projection of nonlinear manifold, if you want. So there's a nonlinear step inside. And now I briefly review something about the wavelets. And it's possible to sampling the signal representing a standard basis, so it's a delta basis if you want, from engineering point of view, or in the frequencies, or Fourier basis. But we learned yesterday that Fourier is not good. So, and the wavelets is a compromise between the two extremes. So the time information and frequencies informations. So, for example, here's the oldest, I think, are series, and it's possible to recognize that it's possible to decompose by using what? Different scale. And so you have possible to consider a multi-scale decomposition of a signal, which means that you have different acceleration of a frequencies time domain, okay? And it's possible to do that. You know that exists a famous theorem about the sampling, because if you have some frequencies is important for us. Why? Because we want to consider where to identify the brain waves. And as I show you in the following. So we have to consider if it's possible to identify some particular bands inside the signal, okay? And how is possible to code in the coefficients of the wavelets. This is the first step. So the first constraint is about the sampling, but this is from the device, okay? And second, we choose a basis in a multi-scale framework. And instead of a Fourier series, you consider wavelet series. And then what you have? We have here represents the time frequencies domain. And look here, if you consider some wavelets, and I don't go through the details, but I think you know wavelets, but if you select some coefficient corresponding to some particular wavelet at some fixed scale and some fixed position, numerically, more or less, you have to consider a block, a region inside the time frequencies plane, okay? Oh, okay, you know, it's not possible to have both compass support for the frequencies and compass support for the time, okay? I use the term numerically, numerical, more or less, and more concentrated inside this block, okay? So it's possible to have some kind of decomposition of a time frequencies plane, okay? And this is our main picture for us. So it's possible to decompose our signal and try to identify the brain waves by using the corresponding well-defined wavelets coefficients, okay? So the idea is very simple. So use a multi-resolution decomposition in order to identify the right blocks inside time frequency plane and then work with these blocks. And this is a different example of a different wavelets. So it's possible to have the same our wavelets, and it's possible to have a rescaling and translation of the same things, okay? And if you have a translation, okay, you change the time, and if you change the scale, also you change the band for the frequencies. If you take the Fourier transform, so we have possible to take the different bands. And okay, roughly speaking, wavelets act as a singularity detectors, okay, and scaling functions, which is the base, and it's possible to build from the a particular basic approximation coded by using a scaling, by using add some details, and that in the details possible to have a singularity detectors, okay? And so this is our first things, and this is an example 1D wavelet transform. Okay, so we have a signal. It's possible to decompose in different details, and it's possible to have a different approximation at different scales. So we have a approximation, different scale, plus time details. Okay, this is a classical framework for wavelets. Then the problem is, what is the best for our case? So it's possible to select some coefficients, some double shear wavelets, some are, for example, very simple and very effective, and or some simulets. So there is a lot of family, okay? But this is a second step in our process. And so it's possible, in principle, to identify by using the wavelet coefficients the delta, theta, alpha, beta, gamma brain waves. Okay, so there is a difference, meaning I don't know if it's clear. For me, it's not so clear, but I don't know if it's so clear from physiological point of view, the meaning of all brain waves. But okay, I accept what I read. And delta waves is a very low frequencies, and so there is theta, and there is also, for example, theta is linked to drowsiness, so means that if you have during the work something more in theta, it's possible to have an index about if the workers have some fall asleep, okay? Alpha waves, beta. So if you look to the band, it's possible to recognize that, okay, more or less, there is some boundary effect, because you are not perfect dyadic decomposition, because for wavelets, the best is to have dyadic decomposition. So means some power to about the different bands of the frequencies is not really here. Okay, 0.5 to 4, it's okay. 4 to 8, it's perfect. Okay. 8 to 14, more or less, because I prefer 16 here, but and so there is something which is not really perfect from the point of view of the dyadic decomposition of weight, but I think this is not a problem. Okay, so this is the brain waves, and it's possible to decompose in principle by using the previous decomposition at high frequencies plane by using wavelength coefficients. Okay,
I
so,
recall, sorry, 5 minutes.
Yes. And now, this is only one experience about is a good for if you have no noise, if good in order to represent our single electrode EEG by using wavelengths. The answer is yes. This is some example, and here I don't know if it's possible to view for you, but there is the percentage about the compression. So we are high rate of compressions, and well, it's possible to well represent our signal. Okay, so seems it's a good object in order to have as sparse representations. Also for denoising, for example, there is a lot of algorithms, a soft art thresholding, for example, and there is a work of Dono's co-workers about the Gaussian noise. Okay, it's okay for standard noise for sparse representations. Artifacts. So there is a lot of artifacts. There is a classical, if you want, EEG, where many channels, but there is an artifact due to the motion, muscular, ocular, cardiac, and so on. So how affects wavelength coefficients? So here, if you want, you have to take some care, and in principle, it's possible to prove by using some micro-local analysis. Micro-local means that you have to define some smoothness of a function by using local information, if you want. So there is some spaces, and it's possible to understand if you have a pattern due to the artifacts. If a pattern affects as ocular, for example, with blinking, is in a sense you have some kind of delta in the time space. It's possible to detect from coefficient, yes. The answer is yes, and it's possible to understand how it's possible to consider how affect the coefficients. So there is some estimates, so local estimates. The same for the frequencies. Okay, for the time, it's possible to do by follow some work of Jafar. And for the frequencies, I think is nothing in a literature, but it's possible to do by yourself by using the same idea. So the idea is, it's possible to consider how the artifacts, if you understand the pattern in the time frequency, affect the coefficients. Okay, and this is our final algorithm, and then I go to some examples. So you take the signal and do the wavelength decompositions, so no pre-processing, and the first thresholding due to the classical thresholding to the Gaussian noise and sparse representation. Then you consider by using statistical properties of the energy at different bands. So in some sense, we have used statistical properties of the coefficients. If you fix some frequencies, and then it's possible to point out some second thresholding, which means it's possible to understand how to change the coefficient in order to remove the artifacts. Okay, and then it's possible to compute more or less the brain waves. So we have two. Instead of a classical algorithm, you have some kind of B thresholding. Classical thresholding and thresholding due to the patterns of the artifact. And I find at the end of the story, it's possible to consider some index and some classification. Is it right? Because we need to start some statistical experiments to collect more data. So there is an example. Here, there is one, I have a lot of this kind of a plot. So you have a single electrode, and the stress means there is some work, okay, is a game, you compute or something like that. In our case, it's only one experiment. And here are some index. And here, what we compute the energy at different brain waves is very, very, very simple by using the orthogonality of the wavelength transform. And it's possible to do that by using the square of the coefficients. It's very easy. And then it's possible to have some index. Some index means that what is the ratio between the energy with different, for example, bands. And if you look here, for example, if you use some index, it's very clear that the variations, so the variability of the index inside the stress is reduces if you consider no stress of baseline. So it's possible to have some index about the variability of the index, and is possible to have some marker about the stress or no stress. Okay, there is 7 index, for example, here. This is the part, and you have to develop this part, but seems is good. Okay, and there is some other example and the conclusion. The conclusion is the following: it's possible to have sunlight in the dark of the problem, because in the darkness of the problem, because we have only single electrode, we have a lot of noise, we have an artifact. It's not possible to have an expert for visual artifact removal, so something like that. I use a classical tools, wave packets, okay? And for experiments, it's possible to understand what is the pattern artifact in the frequency domain. And it's possible also to have some theorem about the effect on the coefficients. And then it's possible to have the thresholding. And then it's possible to develop some index. Next step, okay, learn what is the right index in order to classify in a right way the workers. For example, in our problem. Okay, this is all. Thank you.
Thank you, Giovanni. And now let's see if there are some questions in the chat, or I permit to unmute yourself. So. Okay, there is a question by Annalisa Pascarella.
Hi, Giovanni.
Hi.
I have only more curiosity about, okay, you told that you use only one electrode, but did you consider the possibility to use also a cup as emotive that has 14 electrodes and it's used for BCI, gaming?
Yes, it's possible to do that, but this is our framework. So we prefer to use a very simple device. You use very simple device. Okay.
But I think also emotive is simple, or not?
Yeah.
I know that is also used for psychiatric patients because it's very easy to dress.
Yes. And so very interested your question, because you want to go to the emotive, something like that. If you are single, the electrode is good. Okay, it's particular because you have to go to inside the helmet, so we have some constraint. Okay, but it's very interesting because you want to also to use for a different approach. We have we call brain voice project. So we need for some patients and to understand it's possible to help if you have some diseases as Alzheimer's, something like that, in order to understand if it's possible to help with a voice.
Okay.
So
yeah.
Okay.
In
some sense, we want to understand this is it possible to recognize some brain waves, some states, in order to have some interface for the voice. Okay, and in that case, case, one electrode is not enough. Sure.
Yeah. And now the single electrode, is it in the frontal?
Yeah, frontal.
Okay.
Frontal. So this means also for the artifact, more or less. Is for blinking and some muscular something, no else. Okay.
So they are not heart related artifacts?
Yeah.
Okay, since it's more in front. Okay.
Yeah. Okay.
Thanks a lot.
Yes.
Nice talk. Thanks.
Okay. Are there some other questions or no? If not, I have only one curiosity. But sorry, does the helmet itself does the computation effort, or needs a device where it sends Bluetooth by Bluetooth the
you have to
information?
send something. You have to send.
Okay.
Okay. There is some a very basic filter about Gaussian, something like that. It's a very basic filter for the signal. Okay. Also, roughly speaking, okay, the company we produce this kind of device told us, okay, it's possible also for us to produce also the band alpha. I prefer the raw data. Okay, I prefer to work by myself. Sorry. Okay.
Then it's better.
Yes, I also propose my students during this lesson online, but it's no ethical in order to understand if it's some people or not. I think it's no ethical. Okay.
Thank you.
Collect some data.
Okay, so we can switch to the next talk. The next speaker is Francesca Pitolli from the University of Rome, and she's going to talk about random sampling and solution of the EEG inverse problem.
Thank you. Good morning, everybody. Thank you for inviting me to this workshop. And I would like to present some recent and preliminary results on the use of the random sampling to solve the EEG inverse problem. This is a joint work with Lorenzo Della Cioppa, Annalisa Pascarella, and Michela Tartaglione. And the motivation, this is the outline of the talk. I will give you some motivation that are very similar to the motivation by Giovanni in the previous talk. Then I just recall the forward and inverse MEG problem just to fix notation. Then I will show you how to solve the MEG inverse problem using random sampling. And also I'll try to give some justification of this choice. And then I will show you some numerical tests on EEG synthetic data. And the idea is to solve the inverse EEG, and inverse, to localize neural sources for real-time application like neurofeedback or neurorehabilitation. And especially we have in mind application with the portable devices. So something like also BCI. And so we think about small cap. For this application, magnetoencephalography and electroencephalography are the best choice because they have a high temporal resolution, and especially EEG is very interesting because EEG is obviously we have a cap are more wearable with respect to MEG. So it's very simple. So the idea is to localize the neural sources, so to reconstruct the neuroelectric current flow inside the brain using MEG or EEG devices. And this requires the solution of a ill pose and the condition inverse problem. So if you use usual method to solve the problem, and this method are very often time consuming and have a high computational cost. And so our aim is to find, to construct a method with as a low computational cost. And in particular, we want to reduce the dimensionality of this problem. The forward problem, as usual, means to have a current distribution inside the brain, and then reconstruct the external magnetic field or the electric potential on the scalp or external. And the first step is to construct the subspace. This is a discretized version of the brain cortex of the subject under study, and this is extracted for the MRI images, and then segmented and discretized. So we have n nodes in the subspace, and in each node there is a dipole, which is